Okay, so let's finish up the packet. We're on page 22, and this is going to actually talk about what the lab is about, as well as just looking the last tie-in with our heat. So, calorimetry. This is actually probably something you have experienced, we just maybe haven't put the official word to it. If I took a piece of hot metal, let's just think of our common sense, and put it in some cool water, what's going to happen to the temperature of both objects? Well, you know the hot object's going to cool down, transferring the heat to the water will heat up. So we make these assumptions that we get 100% transfer. So heat lost, remember heat is Q, heat lost is equal to the heat gained. When I lose heat, we say it's negative heat is going to be equal to the positive. So let's say the metal scenario, this would be the metal cooling down, losing heat. Where does that heat go? It goes to the water. And that's another important thing to know, is how the direction that heat flows. So I used to have a question on the worksheet that said your mom in December yelled at you, close the door, you're letting the cold in. And now, is that a real statement? No. You're right, you don't let the cold in, you're actually letting the heat out, because things always flow from a high temperature, high heat to low heat. Okay, so let's look at how these questions, one possible way, and then we'll talk about the lab. So when you're looking at this, I'm giving you two different things. I'm going to give you the heat for enough for the metal. So heat lost equals heat gained. I know this is how I have to do it because it talks about a calorimeter, or a coffee cup. So this final temperature is the temperature for both of those. So really we have to figure out, I just need to use MC delta T, and I know I'm using delta T because temperature is changing. So what do I have enough information? Well, I know the mass of water, I know the specific heat of water, I know the temperature change of water, so I can calculate the heat gained. So we're going to do that first. So this is the heat gained by the water. So what is the mass of water? 250 grams. What's the specific heat of water? Well, right here on the chart it tells me 4.18. Okay, now look at how much did water change temperature. Remember, it's always final temperature minus initial temperature. So how much did water change? 1.4 degrees Celsius. So pull out the calculators, we can do the math, just multiply them. And when we multiply it, it tells me that 1,463 joules. Remember when we do Q equals MC delta T, because specific heat is in joules, our answer is in joules. This is the amount of heat, this was heat gained. And going, okay, well that's half of it. So now I'm going to have to do Q equals MC delta T, because the only way I can identify this metal is to be able to do the specific heat. We just figured out how much energy was gained. Okay, that water gained that much energy. Well, where did that energy came from? It came from the metal cooling down. So that's the quantity of heat that was lost by the metal. So now I know Q. So we're just going to do Q equals MC delta T, but this time let's focus on what we know about the metal. So I know Q for the metal, and it's negative because it cooled. I know the mass of the metal. Okay, I do not know specific heat. That's my unknown. Now look at the delta T for the metal. Final minus initial, so 23.4 minus the 90 degrees it started at. So the metal actually changed by 66.6 degrees, but it's a negative because it was cooling down. And that's good that it's negative, because we have to cancel out the two negatives, because you cannot have a negative specific heat or a negative mass. So now you can just do the algebra, solve for x, and you get that x, which is your specific heat, is 0.399, and your label's joules per gram degree C. So you check up here, so therefore that must be copper because it's the closest to copper. Okay, so question number 2. That's pretty much if you've been on top of everything. We didn't check those 5 problems, but you will turn them in on Friday. And remember, the quiz is going to be similar to those 5 types of problems. So to finish your packet, you only have to finish question number 2. Now let's talk about the lab. So this is the lab, and yes, you have to do the pre-lab questions. And with the pre-lab questions, my suggestion with the lab, let's look at what we're going to do. You can read it through, but a quick summary, I mean, not you can, you should read it through. You're going to take the mass of a can, put about 100 milliliters of water. The water's up front. Just pour it about 100 milliliters, and then go take the mass again. Take the mass of your candle before, take the mass of your candle when you are completed, and that's where you're going to get your data. Okay, we also need to get some temperature changes. So in the lab, go ahead on one of the step 6, it tells you to program the logopros. You do not have to do that. Just get an initial temperature. And then once your 5 minutes is done, we're also changing it from 10 minutes to 5 minutes. Then what you need to do is just get the highest temperature it goes to. And use your temperature probe. So you're going to get your logger probe, get the temperature probe, and get the maximum temperature it goes to. Okay, let's talk about these pre-labs, because what we realized, we're going to kind of blend the 2 parts of this packet. Q, which we calculate MC delta T most of the time. Well, you know what? We're going to make this huge assumption that it's actually the same as the energy. Remember, delta H is enthalpy, which is energy of a reaction. So this is actually how we can go from a physical energy and relate it to a chemical change energy. It's why it's the last activity we're doing. We're bridging the 2 parts of it. So look at what we're doing, these pre-lab. Okay, my suggestion, work on these once you get the candle going. Collect the data so you have plenty of time to work on the calculations. You don't have to sit and do these first and then light the candle. You can go ahead, talk about them, but collect the data and then work on these during that 5 minutes. So look at number 1. Okay, calculate heat needed. This just looks like there's a mass, there's a temperature change. It gives me a specific heat. This is set up for Q equals MC delta T. Okay, then 2 is a different problem. 2A and B is a separate problem. Oh, look at what you have. Balanced equation, and you have a delta H. This is stoichiometry. Now remember, when you calculate stoichiometry, it was a different way to find out how much delta H, which is going to be in kilojoules. So this is an exothermic reaction. It's a combustion producing heat. So now in 2B, look what I'm saying. Well, let's use that heat produced to warm up some water. So we are going to figure out what the final temperature, remember final temperature, here's my hint. Solve for delta T, and then once you know how much the temperature changed, look at over here, you know what the initial temperature is, then you can just add that to it. So we're going to use this concept right here, Q equals delta H. So if you find your delta H, you know Q is equal to delta H. I don't know why I did little, doesn't matter, little, big Q, little q, remember Q's Q. Delta H, so you can do Q equals M, here's your mass, C, it's water, 4.18, delta T, that's your unknown, that's your X, and Q, now you have to be careful because this Q is measured in joules, but this delta H is in kilojoules. You have to change delta H from kilojoules to joules. Okay, kilojoules to joules, multiply it by 1,000. And then you can find your delta T, and once you find your delta T, then you can add that to your temperature to see how much it changed. Okay, let's look at the lab calculations. So this is where you're just going through your data. Calculated mass of water. You're going to subtract how much water was in there. Calculated mass of the candle burned. You're going to subtract how much actually burned. Change of temperature. Guess what? subtract. Okay, now heat is Q. Okay, Q, and look at what you know, MC delta T. The water. Do everything you know for water. You're going to use MC delta T. Heat lost, well, I know heat lost equals heat gained. You're just going to change the sign. Okay, now use your units to help you. So heat of combustion, well, you're going to use your joules you found right here, but this is in joules. So look at what you're going to do. Change your joules to kilojoules. Oops, not kilograms, kilojoules. And then what's it say to do? Divide it by the grams of what produced the heat. Well, what produced the heat? Divide it by the grams of the candle that burned. Okay, then you're going to manipulate it into a different unit, and this is the one we use a lot more often, kilojoules per mole. Same joules, you're still going to do the same thing, same answer from up here, same Q for both times. Change them to kilojoules, but before you do that, you're going to have to change grams of the paraffin, which is wax, by the way. Paraffin is just wax. Change it to moles. That's why on the pre-lab it had you figure out the molar mass, and then divide your kilojoules by your mole. Now I'm going to tell you this mole value is going to be really, 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 really small, so don't let that freak you out. But when you divide by a really small number, that's what's going to get that number larger, and here's what the real value is, so it should be a fairly large number. Okay, so on the calculations, this lab, you're actually going to make a lab poster, and on that poster is where you're just going to sum up all of the information. Now these lab sheets, I need you to you're going to tape to the back of the poster one completed lab, but I need to see both sides. I'm not going to flip it over, so we're really going to use two lab sheets. Somebody have it nice and pretty. You tape the front side with all your pre-lab work and data, and then somebody else is going to tape the back side that has all your calculations and go through and answer those questions. I definitely suggest on your conclusion, look at a little bit of error analysis, because one thing we make this huge assumption, especially in this lab, that 100% of the energy coming from that candle is going into the water and being used to heat the water. And discuss with your group if you really think that that's a very possible thing, or is that a good assumption, or is that maybe being a little bit far-fetched looking at our high school lab scenario. Okay, so you should be able to finish all of this in class today. If there's any questions, I know that you're in capable hands, and that you also know you're my very good bunch, and you guys can figure it out. And I will see you on Friday.